we have seen with this voltage amplifier, we fixed voltage to voltage of this structure. So we had a voltage from the source, we had a voltage across the load that we wanted, we needed a voltage amplifier, and we know from the previous lectures that we then need to fix A to a fixed value and keep B, C, and D 0 of the transmission 1 matrix. And that we have achieved by using what we call output voltage sensing, which is also called output parallel feedback, and input voltage comparison, which is also called series feedback. So voltage comparison is series feedback at the input, and voltage sensing is parallel feedback at the output. Now, with these words, we have the keywords for making all amplifier structures. We didn't look yet at the implementation of the feedback networks, and that is what we will do here also. So here, you see that my voltage attenuator is a transformer. It senses the load voltage here, and it places a copy of the source voltage in series with the source voltage. And here is a nuller that nullifies the difference. If you look at the properties of this amplifier, you can say, well, we have port isolation if the controller, if the nuller and the nullator and the narrator are completely isolated, then the whole thing can be isolated. So we can have port isolation with this structure. We can have inverting or non-inverting transformer. It only depends on how you connect your transformer. If you flip the transformer the other way around, because this is just condition 0. So if you flip one of the windings of the transformer, you have inverting or non-inverting transfer. The gain can be made less, equal, or larger than unity. It's only defined by the winding ratio of your transformer. A non-energetic feedback follower. Non-energetic means that in the feedback network, there is no energy storage and no power losses. So that is also the case for short circuit and open circuit. And here you see we have from the output to the connection from the output here to the series with the input. So this is parallel voltage, and the whole voltage parallel, the whole load voltage is placed in series with the source. So the gain is unity. So this is called a voltage follower. But now you see that the sign of the load voltage is equal to the sign of the source voltage. And we have no port isolation because there's just a connection in between. So no port isolation, non-inverting, and the gain equals unity. Another implementation, passive feedback. So we have a passive voltage attenuator. So we create an attenuated copy of the load, and that copy should be equal to the source. And here you have the reciprocal transfer of this network is the voltage gain. Well, that is there. So we have no port isolation. Again, you see a connection between the output and the input port. It is non-inverting, and the gain is larger than unity because this number is always larger than unity. So 3 possibilities for what we call a negative feedback voltage amplifier. Now, the next one is voltage in, current at the load, and then we call it a transadmittance amplifier. We fix parameter B of the transmission 1 matrix, and we need to do it. Let's say if we have voltage input, we have current output. So at the output, we need to sense the current. Output current sensing, called series feedback at the output. And input voltage comparison, that is the same as the previous one, so still series feedback at the input. And here we go. The non-energetic version uses a gyrator, but unfortunately we have no practical components for that. It senses the current. You see, it is placed in series with the load. So it senses the current is equal, and the gyrator converts current to voltage. So it places this voltage anti-series with the source, which means that we have a transfer from voltage to current accurately established. So there is port isolation, as long as the nuller, of course, has a port isolation in it. And it can be made inverting or non-inverting. You just flip the connection at one side of the gyrator. And there's no unity gain version because the gain is like, let's say, not dimensionless. So we cannot talk about unity gain. So passive feedback, we have this one. We measure, and we do it here in the other terminal. See, if this IL is flowing in one terminal of the narrator, it's also flowing in the other terminal of the narrator. And here we create a copy of the source voltage across this impedance, and then we place it in series with the source and nullify the difference again with a nuller, and that makes us establish a inverting transadmittance gain. So we have no port isolation, and we have an inverting transfer of this structure, passive feedback. Next one, current input, voltage output. It's called a transimpedance. So we are going to establish the parameter C of this one. So we need to have the voltage established at the output and the current at the input, which makes, again, like the first one, output voltage sensing or parallel feedback, and input current comparison, which is also parallel feedback. So both parallel feedback at the input and at the output gives us the transimpedance amplifier. Let's do it. So we have the non-energic transimpedance amplifier. It uses the gyrator, but now gyrator is placed differently. You see, it is now measuring the voltage in parallel with the load, converts it into current that is subtracted in parallel from the source, making the result here, well, this nuller nullifies the result so that the input current will be 0 and the voltage here will be 0, and the transfer will be equal to 1 over G if G is the constant of the gyrator. So it has port isolation, again, like the previous one, inverting or non-inverting. It's just flipping one of the sides of the gyrator to make it inverting or non-inverting. Passive feedback, we can make it in this way. Parallel feedback at the output, so we measure the voltage in parallel, and parallel at the input. And since this voltage equals 0, because there's a nuller here saying this should be 0, we have exactly the load voltage completely over this impedance, and no voltage across the source impedance. So all this current flows through the feedback and creating minus Z times the input current as output voltage. So the transfer is given by this one. We have no port isolation, and the thing is non-inverting. So we have seen, and oh, sorry, the last one is the current amplifier. We need to establish D. Well, you can now guess we need to do current at the input and we need current at the output. So we combine this for the input and this for the output, which means we have output current sensing, series feedback, input current comparison, parallel feedback. You see the words voltage and current are uniquely coupled to series or parallel. Non-energic, then we use the transformer again, but now we use the transformer to sense the load current. You see the transformer, this winding is placed, the secondary winding is placed in series with the load. So it has the same current flowing through it as the load. And then the current at the other wire is subtracted from the source. So it's in parallel, anti-parallel, making that we can create the condition here I equals 0, and then we have exactly the transformer ratio as transfer of the amplifier. And again, we can have port isolation, we can make it non-inverting or inverting, we can make a gain less, equal, or larger than unity, just depending on the ratio of the windings of the transformer. The follower, the unity gain current amplifier, we can make it here. We see we are sensing the load current, but in the other side of the wire, we are sensing the load current and completely subtracting it from the source, completely subtracting, having 0 here, if the thing is completely accurate and having unity gain transfer. So we have no port isolation, non-inverting, and the gain equals unity. Later on in the next session, you will see why I use passive or non-inertics explicitly in the word, because they have very important different properties. Passive feedback amplifier, here we measure the current, and here we have a current divider. So the current IL is larger than IS. IS is just a part of it, this copy, and we subtract the copy from the source current and have it 0 as a result, giving us the transfer as given here in the formula. We have no port isolation, non-inverting behavior, and a gain larger than unity.